Let's determine which of these molecules is least likely to form hydrogen bonds with a water molecule. As you may know, water molecules are highly polar molecules with an extensive network of hydrogen bond interactions in a sample of water. So let's just clarify, hydrogen bonds are special dipole-dipole interactions, very strong ones, where you have a hydrogen atom covalently bonded with one of these very electronegative other atoms, like nitrogen, oxygen, or fluorine. Let me draw my one water molecule so we can compare, see if which one of these is not going to interact hydrogen bond style. So if you draw the Lewis structure for H2O, you get something like this. It would help if I drew three-dimensionally, but to keep this brief and simple, right? So these are all approximately 109-degree bond angles. Okay, you got to try to imagine that. Because oxygen, which is over here, 3.5 on the Pauling scale, and hydrogen is there, 2.1. There's a pretty significant polar bond there. So this shared bonding pair is going to be more on the oxygen side, giving this side slightly negative charge and the hydrogen side slightly positive charge, because if that one electron is on one side of the hydrogen, the only other thing there is the proton, right? We're going to need something to interact with these partial sides. Oxygen has these two lone pairs, so I'm going to just focus on that side. All right, before I go on, let me copy this. I don't have to redraw this. All right, let's take a look at our ammonia molecule, NH3. If you draw the Lewis structure, you'll get the nitrogen in the center with, yeah, this would help much more if this was in 3D, because you'll see that doesn't have complete symmetry. Okay, anyway, nitrogen, again, is one of these very electronegative elements. You're going to get this unequal sharing of shared electrons. So you're going to get the one side of the ammonia molecule being partially negative, and then the sides where the hydrogens are, they're going to be partially positive. And that is what's going to cause or allow for hydrogen bond interactions. So there's your hydrogen bond. A is good, so that's not the answer. Let's go on to, let's skip B, because B, it's a little tough to see, so you have to draw the Lewis structure. So I'll get to that later, because I know that's going to be the answer. Hydrogen fluoride is one of the most polar molecules. It is the most polar bond on that list, so that is for sure going to make a hydrogen bond with this. Now, let me share with you, students often think sometimes hydrogen bonds are like that. When a hydrogen is bonded to a very electronegative element, that is not a hydrogen bond. That's a covalent bond. All right, so I can see how that's confusing and how that can mix students up. You need a hydrogen bonded to an electronegative element or atom, but that is not a hydrogen bond. That's a covalent bond. They're very different things. Hydrogen bonds are the interactions between molecules that have that. It can even be in the same molecule when you're talking about larger molecules like proteins. But at this level, you're usually talking about interactions between molecules, or at least between different parts of a molecule. Okay, what were we doing here? Fluorine covalently bonded with hydrogen. So this is what you need. You need a hydrogen covalently bonded with a very electronegative atom. But that doesn't mean that's a hydrogen bond. This sets up the molecule to become dipole enough to make hydrogen bond interactions with other of its kind. So here again, fluorine, being the most electronegative element, is going to unequally share. So this side is going to be partially negative and this side is going to be partially positive. See how we have this scenario now? We can have, that's your hydrogen bond. Okay, I think we're getting the hang of this. Let's go on to hydrogen peroxide, H2O2. Okay, so here's my water molecule again, hydrogen peroxide, just drawn two-dimensionally here, just for ease. Remember, hydrogens do not go in the center. Again, these are all three-dimensional, 109-ish angles on this one again. So, but here we go. We have another hydrogen, another instance where you have a hydrogen covalently bonded to a very electronegative element. So again, this side is going to be slightly negative, where the oxygens are in the lone pairs, and the hydrogen side is going to be partially positive. So now we have that opportunity for hydrogen bonding to occur between the water molecule and, in this case, hydrogen peroxide. Okay, let's take a look at our final one, which is methyl chloride, or chloromethane, if you will. Oh no, where'd my water molecule go? I lost it. Alright, I got it back. So here's my final water molecule. Now this last one's a bit tricky because if you were just looking at the formula, which is, let me go back to that. A student might think, well, hey, chlorine is really electronegative right down there, 3.0, and it looks like it's connected to that H, but it's really not. It's really a methane molecule with a chlorine swapped, a hydrogen swapped out for a chlorine. So if you follow the Lewis structure rules, you know that chlorine is going to go in the center. All right, so here's a methane molecule. Okay, when you take that H out, you get what we call a methyl group, and you're just swapping that H out with a chlorine. So notice we do not have a connection, a covalent bond with that chlorine. All right, rather does not fit the bill. This is no hydrogen bond. Nothing, no H bonds here going on. So the answer is B. All right, so hopefully you remember that misconception, because I do see that, and I can see how it confuses students. Hydrogen bonds are not hydrogens covalently bonded to electronegative elements. All right, and then this one here, draw out the Lewis structure. Don't just assume they're connected in the way they're written in the formula.